Hello, everyone, and welcome to AP Chemistry Unit 2.7, VSEPR Theory and Orbital Hybridization. Today, we're looking at Part 2, which is the orbital hybridization part. We're going to learn about what it is and how it works. We're going to learn some steps to predicting what the hybridization of an atom and a molecule is, and then we're going to look at some AP-style multiple-choice questions that will help you prepare for your own tests coming up. So I hope you're ready for it. It gets kind of weird talking about orbital hybridization if you've never done it before, but I hope you're ready, and let's get started. In our previous episode on VSEPR theory, we looked at these essential knowledge statements before, and we got down to here where it said hybridization of valence orbitals for atoms within a molecule or polyatomic ion. And then it says, the terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angles are 120. For sp2, the bond angles are 120. And for sp3, the bond angles are 109 and a half. Okay. And then we get a couple more statements. We'll you'll see what they mean in a little bit while. There's a couple of inclusion statements that we only have to know about sp, sp2, and sp3 hybridization, and so on. We're going to talk about sigma and pi bonds a little bit next time. So let's get started with a little bit of the theory. Again, it gets kind of weird in here, but hopefully this will make some sense. So let's review the bond energy kind of deal. Remember that when two atoms come together to form a chemical bond, they actually move to a lower energy place. This situation out here is kind of stressful and high energy. They haven't found each other yet, but they're moving toward each other, and as they do, they settle into a lower energy state that has a very specific bond length and a very specific bond strength, the bond energy, the energy that's given off. Now we got to talk about what happens to those orbitals while that's happening. Now, this diagram does a little good job of showing that the orbitals are slightly changing and they're slightly overlapping. And that hopefully is that's an underlying principle here. If an orbital moves to a lower energy state, that means the electron that's in that orbital has a lower energy. And we've talked sometimes about how electrons have wavelengths and frequencies just like photons of light do. And if their energy is decreasing, that means their frequency is decreasing and their wavelength is increasing. And that changes the shape or the path at which those electrons, this is speaking loosely here, move around the nucleus. And so the shape of the orbital actually changes. So what is hybridization? Hybridization is what happens when two atomic orbitals combine to form a new molecular orbital of lower overall energy. Okay, the old shapes are gone, the shapes of the S's and the P's and the D's, they're gone, but new shaped orbitals change and come in their place, all right? I like to use the word morph in class because we've all seen movies where some character morphs into some other character, and they're still the same character, but they look different. They have a different size or a different shape, and that's what orbitals are doing. The theory goes really, really deep. The nice thing is we don't have to know all of that theory for our AP chemistry exam. We have to know how to predict the hybridization and know that it exists. But let's check it out. So hybridizations of some simple S and P orbitals for like diatomic molecules, they come together and they overlap, and so their orbitals change slightly. Here we have an S, one S orbital and a 2p orbital, and you can see when they get together, they kind of morph into something that's a little different, a little wonky looking. And you get a couple of p orbitals coming in, and they morph into this type of orbital. Again, it's kind of wonky looking, but it's kind of like you can see the family resemblance from both sides, but the end result is different from the two original parent orbitals, I guess you could say. Okay, so let's work through the 5 main hybridizations and imagine what situations they would need and why they might happen. So let's start with the simplest one, sp hybridization. So imagine for a moment that I am a beryllium atom, and I'm a beryllium atom and I want to combine and bond to 2 chlorine atoms. Okay, that means 2 single bonds. I only have 2 valence electrons to start with, so they're going to pair off and that's it. So I really only need 2 bonds, right? So what I need is 2 orbitals that are equivalent. Okay, it's hard to bond with the 2s orbital, and sometimes you have elements with 2s's and 2p's and they look different. We need orbitals that are the same and of lower energy. So what beryllium will do is it'll actually take one of its s orbital and one of its p orbitals, and only one of each because it only needs 2 bonds. So it'll take those two, and notice the s is at low energy and the p is at high energy. It makes 2 orbitals that are somewhat of an average between the energies of the first two. Okay, they look kind of like lopsided mushrooms. Okay, one side bigger than the other one, but they're identical, and they can actually orient themselves across 180 degrees from the nucleus. And this, because they're taking up maximum space opposite of each other, it actually gives some credence to the idea that this is a linear structure with bond angles of 180. Now, an atom will only hybridize as many orbitals as it needs to make the bonds that it needs to make. So sometimes there are orbitals that are left out. And if you only need to make 2 bonds, you take an S and a P and you hybridize them, you morph them into new things and do your bonding with that. Those then overlap with the chlorines that would come in from the sides. Now, let's say I'm a boron atom and I would like to make 3 bonds, one in each direction. So I see 3 fluorines, I want to bond to them. Well, what I'm going to do is I'm going to take my s orbital and 2 of the p orbitals. I've got 2 electrons in the s and 1 in the p. That's 3 total valence electrons, but each one of them needs its own hybridized orbital. So I'll take this one, and this one, morph them together, and suddenly I've got 3 of equal energy that are higher than this one, but lower than this one. The remaining s orbital is left out. And now I have 3 identical orbitals that can magically arrange themselves 120 degrees from each other around that central atom, leaving behind this orbital right here. It's not being used. There's nothing in there. Theoretically, it's there, but there's no electrons in there, so it's kind of just out there, not being used. And so we get sp2 hybridization, 1s and 2 p's. All right, a very common one is, what if I was a carbon atom? Heck, I'm made of a ton of carbon atoms. And a lot of the carbon atoms inside me are sp3 hybridized carbons. Here's why. Because carbon has 4 valence electrons and it likes to make 4 bonds. So great. So it will need an orbital. So we've got 2 here, 1 there, and 1 there. It'll take all 4 of those orbitals and morph them all together to create 4 hybridized orbitals. Notice they look like lopsided mushrooms, partly like a P and partly like a round S. And those can actually arrange themselves 109 degrees from each other in a tetrahedron, which is why carbon oftentimes makes this tetrahedral type structure. So again, these 4 have somewhat in the middle of energy of these guys. Notice that energy is also lost in the process, so it's not a full-on average, a complete average. But that's sp3 hybridization. Now, I will tell you, there's 2 more types of hybridization, and I'm going to show them to you here. But we are told by the College Board that the last 2 are not going to be tested, but it's good to know that they exist because it might not be an AP exam, but you might run into them. Let's say I have like a phosphorus pentafluoride. It needs to make 5 bonds. How's it going to do that? Well, it's going to start with its S. It's going to hybridize its 3 P's, but that's only 4. And so we need a 5th one. And so elements that are in the 5th or the 3rd row down, including phosphorus and anything below it, actually have d orbitals nearby that they can pull in and hybridize themselves. So this one will actually do S, the 3 P's and a D, so we'll call it sp3d. Sometimes you'll see it as dsp3. And something like an SF6 can actually hybridize 6 orbitals, the S, the 3 P's, and 2 D's to get to a total of 6. We're not going to go beyond that. I don't even think that exists. Maybe it does. So you can leave me a correction in the comment. But again, we're going to focus on these top 3, but you might in your chemistry travels see those. A quick summary. And that is, all right, we got 5 types of hybridization. Which orbitals are being used? Notice the S is always used first, followed by however number of P's you need. If you run out of P's, you got to start hybridizing the D's to get anywhere between 3 and 2 and 6. And those correspond to the 5 electron pair geometries: linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Before we get into the questions, I want to share with you a document that I typed up a long time ago, and I share with my in-class students on a yearly basis. All right, and I titled it "Important Notes About Hybridization" because you're going to have to answer questions about it. So, number one, effective pairs of electrons include those that are lone pairs and those that bond two atoms together. So you have to be able to count how many effective pairs are there because effective pairs are going to need their own space and their own hybridized orbital. So lone pairs are effective, and the ones that bond atoms together are effective. In multiple bonds, only one pair of electrons is considered an effective pair, since only one pair is actually required to bond the two atoms together. The other pairs are added into the arrangement as pi bonds. Now, in our third section, we're going to talk about sigma and pi a little bit more, but here's a brief introduction to it. So, if you have a double bond, only one of them is hybridized. If you have a triple bond, only one of them is hybridized. The other two are extra. The effective pairs of electrons all act together to decrease the overall energy of the molecule. They do this by hybridizing. Unused orbitals do not hybridize. They're just empty and theoretically there, but not doing anything. Hybridization is the combining of s and p and sometimes d orbitals to create a set of identical new orbitals that are an average, and I use that term loosely, it's an average, of the original orbitals. The resulting orbitals have a higher energy than the s orbital and lower energy than the p orbitals used. Okay. Number of effective pairs. You have 5 possibilities: 2, 3, 4, 5, or 6. They correspond to the geometries we already saw, and then these hybridizations, anywhere from sp up to d2sp3. So what are you supposed to do? When we get to questions like this, they sometimes take a couple of steps. First, if you don't have the Lewis structure, you should draw it. All right, make sure you have a valid Lewis structure that you can look at, because you have to count the bonds and the lone pairs. Determine the arrangement of electron pairs using the VSEPR model. Okay. Then determine the number of effective pairs on the central atom. Specify the hybrid arrangement that will satisfy those effective pairs. We'll look at some examples real quick. In a multiple bond, one of the bonds is a hybridized orbital. Therefore, a multiple bond will always have one sigma bond. That's the hybridized bond. And the others will retain their p orbital structure and delocalize above and below the sigma bond. More detail on that in our next episode. Let's look at a already worked out example. What's the hybridization of each atom in the structure? Okay, so we got the structure here, and then we have the molecular model version over here. But let's pretend for a moment we don't have that. When you're trying to find, for example, the hybridization around, say, this carbon right here, you look at the structure and say, how many bonds does it have? 1, 2, 3, 4. That's 4 single bonds. I don't see any lone pairs on that carbon, which makes sense. And so I have to think to myself, okay, I have 4 effective pairs. And that leads me to say it's going to be a tetrahedral arrangement. And because it has 4 bonds, it needs 4 hybridized orbitals, or the sp3 hybridization, which we have over here. That's what it's showing. Now, this carbon right here is sp2. So why? It has 4 bonds itself, right? Well, one of those bonds is a double bond. And so we have a single bond, and a double bond. The first in a double bond is hybridized. The second one is not. It's not in this way anyway. And so we have 1, 2, 3 effective pairs, essentially, not 4. And so that makes it a trigonal planar around that area, and that would be sp2 hybridized. Okay. We have an sp3 listed over here for the oxygen, and that's because in the original structure it has 2 bonds and 2 lone pairs. Those lone pairs are effective because they need their own space and they do affect the shape of the molecule. So again, 4 hybridized orbitals are needed, and that's also sp3 hybridized. Just to show you another example, this is PF5, and all 5 fluorines are attached to the phosphorus, and so that phosphorus needs 5 identical hybridized orbitals, and so it will end up being dsp3 or sp3d because it has to have 5. It'll use the S, the 3 Ps, and a D. Now, we are told we don't necessarily have to know this hybridization for the AP exam, but you might need to know it for your other Gen Chem course or anything like that. Before we get into the AP style questions, I just wanted to mention again, feel free to copy this down or take a screenshot of it if that's helpful for you in your chemistry travels. Okay, here we go. We're going to race through some multiple choice questions. What geometrical arrangement is associated with orbitals that are sp2 hybridized? So here we're going in reverse. We have the fact that it's sp2, so we have to think to ourselves, one s and a couple of p's. That's 3 effective pairs that we're going to need in whatever structure this is talking about. So 3 effective pairs, that makes it a trigonal planar structure. So find a way for yourself to remember that. Here we have another one. The hybridization of the carbon atoms in the molecule represented above can be described as, here, this is the other way again. So 1, 2, 3, 4, they're both the same with 4 bonds each. That means we're going to need an s and all 3 p orbitals, so that's sp3. Once you kind of have your system down, these go pretty quickly. Now this one, it says the hybrid orbitals of the carbon in CO3 2- are. Now for the sake of time, I went ahead and drew the Lewis structure over here. So if you are in a question like this, you should take the time to draw the Lewis structure, unless you're just have done enough that you can picture it in your head. Some people can, but if you can't picture it in your head, draw it. Just take the time to do it. And then I see, because of that, I see a double bond here. So 1, 2, 3 effective pairs. Remember that fourth one is not. So sp2 is the hybridization of that one. Here's another one where the hybrid orbitals of nitrogen in N2O4 are, can't picture it, draw it. Take a moment, get the Lewis structure down on your paper in the margin, and then you can start counting effective pairs. So 1, 2, 3. Again, there's a double bond, so don't count the second one. So this is also sp2 hybridized. All right, and I drew the Lewis structures on the next ones as well, because we're focusing on hybridization in this episode, not the actual drawing. So which of these molecules has a shape related to a tetrahedron or has sp3 bonding? I drew all the Lewis structures, and it's getting a little more complicated because there's more structures to consider. So I'm looking for sp3. So there's 4 bonds, that's sp3, and then 3 bonds and a lone pair, that's sp3. So both of those are sp3. This one is dsp3. This one's only sp2 because we have a double bond. And this is going to be sp, because remember, a triple bond only has 1 hybridized orbital, and then the other side. And then this is sp3, but that's only sp, so this doesn't count. So I'm going to pick letter A. You'll get a chance to pick your own on the next one. So get ready to pause the video. Which species contain the central atom with sp2 hybridization? Take a moment, pause the video, and see if you can guess this one. All right, and if you guessed C, that is correct. We have a effective pair here, an effective pair there, and 1 effective pair there. That's 3 effective pairs for sp2 hybridization. Just for fun, let's do another pause the video. Sulfur forms the following compounds: SO2, SCl2. Let's get the autofocus going. There we go. All right, so SO2, SCl2, and SO3. There's the structures. Which form of hybridization is not represented by these molecules? All right, so again, you have to draw the Lewis structure. You have a minute and a half on these multiple choice questions, so if you know it's going to take you a long time, just skip it and come back to it. So that is right there. That should be sp2. This is sp3, and this is also sp3. So that means sp is not shown in either one of those, any one of those. So sp. All right, we just got a couple more. What is the hybridization of the carbon atoms in the molecule of ethine? Okay, and again, we have each carbon has an effective pair here, and then 1 effective pair there. Even though it looks like 3 bonds, it is 3 bonds. Only one of them is effective. So 2 effective pairs, that makes it sp. And the last one I have here, sometimes they like to make it a little more difficult by having more than one to consider. So we just have to pick CH4 and H2O. And if you haven't drawn them or can't picture them, draw them and see if you can decide what the hybridization of the carbon and the oxygen are in those two. All right, we've seen a couple before, and these are both sp3. If you draw them out and get them correctly, they're both going to be sp3. So these are the type of questions that you're probably going to be asked. There's probably not a lot of them on the AP exam, but there's enough that you're going to want to know the steps on how to do them. So make a note of that if that's helpful for you. So I hope you found this video helpful on hybridization. It's very visual to get started, but once you get down to it, there's a set of concrete steps that you need to use to predict hybridization. If you have any questions, send them to me in the comments. And in the meantime, happy studying and have a great day.